Good afternoon, students. This is B. Srinivasa, Department of Electronics from TJPSC College. Welcome back to our session. Today we are going to discuss about logic circuits. Here the logic circuits are of two types. First one is the combinational logic circuit, and second one is the sequential logic circuits. Here the combinational logic circuit, a logic circuit whose outputs can be depending upon present inputs at any time. Whose outputs can be depending upon present inputs at any time. Then the logic circuit is known as the combinational logic circuit. That means here this is the logic circuit. We can apply the inputs. And get the outputs. Is produced by output. Here the output is can be depending upon the present inputs. Here we can apply inputs. In that inputs it can be depending upon the output. Then the circuit is known as the combinational logic circuit, whose outputs can be depending upon present inputs at any time. Then the circuit is known as the combinational logic circuit. And next one is the sequential logic circuit, whose outputs not only depending upon the present inputs but also depending upon the previous history of outputs. The circuit diagram of the sequential logic circuit. This is the logic circuit. Here the produce the output. Those output can store the one memory element. In that memory element, it can store the one binary bit of information, either 0 or 1. In that output, also applied to the input. And present input, sequential logic, whose output not only depending upon the present input but also depending upon the previous history of previous output. Whose output not only depending upon the present input but also depending upon the previous history of output. Those output are connected to the input. Here consider the present input and previous history of output. Here consider present input and previous history of output. Then the output is produced. That type of circuit, logical circuit, is known as the sequential logic circuit. Okay. Combinational logic circuit, whose outputs can be depending upon present inputs at any time. Then the circuit is known as the combinational logic circuit. And here the sequential logic circuit, whose outputs not only depending upon the present inputs but also depending upon the previous history of outputs. Those outputs are connected to the inputs. Here consider the present inputs and previous history of outputs. Then the circuit is known as the sequential logic circuit. Okay. Here the combinational logic circuits are adders. Combinational logic circuits are adders, subtractors, multiplexer, demultiplexer, encoder, and decoder. Those are combinational logic circuits. These circuits can be depending upon the present inputs only. We can apply the present inputs, then the output is produced. Okay. Here the sequential logic circuits. Here the example for the sequential logic circuits are the flip-flops, counters, registers. Those are the sequential circuits. These are the sequential circuits. These are the combinational logic circuits. Okay, first of all, we can discuss the combinational logic circuits. Combinational logic circuits. Combinational logic circuits. In combinational logic circuit, we see the adders. Adders are of three types. First one is the half adder, and second one is the full adder, and third one is the parallel adder. Parallel adder. Adder, it can perform the sum operation. Okay, subtractor, it can perform the difference operation. Okay. In logical circuit, any information here, the inputs and outputs can be represented in the binary form only. Here we can represent it binary form means either zeros or ones. Here the inputs and outputs, those are can be represented by either zeros or ones only. Half adder. Half adder. Definition for the half adder. A adder which add 2 bits at a time, then the adder is known as the half adder. A adder which add 2 bits at a time, then the adder is known as the half adder. Okay, we can draw the block diagram of half adder. Block diagram of half adder. In half adder, it consisting of definition for the half adder means definition for the half adder is a adder which add 2 bits at a time. Here the two inputs, those are A and B. Those are the inputs. In this adder, we can add 2 bits at a time. Then the adder is known as the half adder. Half adder. Here the outputs can be produced by sum. It can be represented by S, and second output it can be produced by carry. Carry. This is the block diagram for the half adder. And next one, truth table. Truth table for the half adder. It consisting of 2 inputs. Each input can possible combination either 0 or 1. 2 possible combinations consisting of 2 inputs. How many possible combinations? 4 possible combinations. Those are 0, 0, 0, 1, 1, 0, 1, 1. Here we can take the inputs and outputs. Here the inputs are A and B. Here outputs, sum. Here the outputs, those are the outputs. Those are the outputs. Sum, carry. Outputs. Okay. How many possible combinations? 4 possible combinations. Those are 0, 0, 0, 1, 1, 0, 1, 1. In this adder we can do the 2 bits at a time. A adder which add 2 bits at a time. A adder which add 2 bits at a time, then the adder is known as the half adder. Okay, we can follow the binary addition rule. Binary addition rule. In the binary addition rule, 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. 1 plus 1 is equal to 1, 0. Here 0 can write in the sum, and 1 can write as carry position. Okay. First of all, 0 0. We can add 0 0. Here the inputs A is equal to 0, B is equal to 0. Then the output sum is equal to 0, carry is equal to 0. And next one, if A is equal to 0 and B is equal to 1, then the output sum is equal to 1 and carry is equal to 0. Here those inputs 0 and 1. Sum is the 1. There is no carry. It can be represented by 0. And third case, if we can apply the A is equal to 1 and B is equal to 0, A is equal to 1 and B is equal to 0. At that time, sum can be represented by 1, there is no carry. Sum can be represented by, there is no carry. And fourth case, if we can apply the 1 1, A is equal to 1 and B is equal to 1, then sum can be represented by 1 and carry also. Sum can be represented by 0 and carry represented by 1. Here 1 0 can return as 0 can return in sum position and 1 can return as carry position. Okay, 1 0. Okay, we can write the logic expression. If A is equal to 1, then A bar is equal to 0. Here in this column, A is equal to 0, we can return as A bar. B is equal to 0, we can return as B bar. Okay, A bar into B bar. This is the min term. Next, if A is equal to 0, we can return as A bar. And B is equal to 1, we can return as B. A bar into B. And next, third case, if A is equal to 1, we can return as A. And B is equal to 1, then B bar is equal to 0, B bar, A into B bar. And fourth case, if A is equal to 1 and B is equal to 1, A into B. Okay, we can write return as expression term. We can return as expression term in min term. Okay. See the sum column. In the sum column, here the output is 1, here also the output is 1. Sum expression 1. Corresponding the expression, we can take it as the expression A bar into B plus A into B bar. In this expression is called as a SOP, sum of product. That the product terms can be written as sum. That form is the sum of product form. Here the product terms are expressed in sum or add operation. Because then the form is known as the sum of product form. Okay, in this expression, already I told you A bar into B plus A into B bar. In this expression, we remember that A bar into B plus A into B bar. In this expression, XOR operation, A into A XOR B. That's the sum expression. Sum expression is A XOR B. And second one, in the column, in the carry column, we see here the output is 1. And the corresponding expression we can take carry. Corresponding expression A into B. Here the carry expression is A into B, and the sum expression is A XOR B. Okay, first of all, definition for the half adder. A adder which add 2 bits. A adder which add 2 bits. There are the 2 inputs A and B. Okay, which add 2 bits at a time. Then the adder is known as the half adder. Here the outputs can be represented by the sum and carry. Here the 2 inputs. How many possible combinations? 4 possible combinations. Those are 0 0, 0 1, 1 0, and 1 1. Okay, here the sum and the carry, those are the outputs. Okay, we can write as the sum expression and carry expression. We can draw the diagram for the half adder. We can use for, in which case we can use the outputs sum expression and the carry expression. Sum expression S is equal to A XOR B, and the carry expression C is equal to A into B. Here the inputs in the block diagram, here the inputs can be represented by A and B. A and B. Here the inputs, those are the inputs. This is the outputs. We can draw the diagram for the half adder. In which case can be used? Simply, we can see the expression sum is equal to A XOR B. Here the two inputs, in these two inputs we can perform the XOR operation. That's why we can use for the XOR gate. This is the XOR gate. Here the XOR gate output. Here XOR gate input we can apply the A and B. One input A and another input B. Okay, and next output carry. In the carry expression, we can represent A into B. We can perform the product operation or multiplication operation. In which case can be used? We can use for the AND gate. And the AND gate can perform the product operation or multiplication operation. Here we can apply the inputs. The inputs A and B. Those are the inputs. Here inputs are applied to the AND gate. Here the inputs A, B. Here inputs A and B. These inputs are applied to the XOR gate and AND gate. This is the internal circuit diagram for the half adder. We can see the block diagram. In this block diagram, two inputs, those are A and B. Those are inputs. Here the outputs can be represented by sum and carry. Here the inputs and outputs. This is the internal circuit diagram for the half adder. Here we can use for in the half adder we can use for the one XOR gate and one AND gate. Okay. In this adder we can add 2 bits at a time. Then the outputs is produced by can be written as sum and carry. For example, we can take if A is equal to 1, and B is equal to 1. Here A is equal to 1, B is equal to 1, we can apply the XOR gate. A is equal to 1, B is equal to 1. And these inputs are also applied to the AND gate also. At that time, sum can be produced by 0 and carry produced by 1. Okay, we can see. XOR gate, according to the XOR gate definition. What are the XOR gate definition? If both the inputs are different, then the output is high, otherwise it is low. Okay, we can apply the inputs. Here A is equal to 1 and B is equal to 1. According to the XOR gate definition, if both the inputs are different, then the output is high, otherwise it is low. Here we can apply A is equal to 1 and B is equal to 1. Here both the inputs are same, then the output is 0. Here the sum is 0. And the carry, if we can apply the AND gate, here the inputs A is equal to 1 and B is equal to 1. According to the AND gate definition, both the inputs are in high. Then the output is high, otherwise it is low. Okay, here AND gate, according to the AND gate definition, if we can apply the A is equal to 1 and B is equal to 1, here both the inputs are in high position, then the output is high. At that time, the output Carry can be produced by 1 and sum produced by 0. Okay, suppose if we can apply 0, 0, A is equal to 0, B is equal to 0. At that time, sum is equal to 0, carry is equal to 0. If we can apply the A is equal to 0 and B is equal to 1, A is equal to 0 and B is equal to A is equal to 0, B is equal to 1. In this condition, A is equal to 0 and B is equal to 1. In this condition, at that time, sum is in high position and carry is low position. Okay, we can see the XOR gate inputs. If we can apply the A is equal to 0 and B is equal to 1, according to the XOR gate definition, if both the inputs are indifferent, then the output is high. Both the inputs are different, then the output is high. Otherwise, it is low. If we can apply the AND gate here, A is equal to 0 and B is equal to 1. According to the AND gate definition, both the inputs are in high, then the output is high. Otherwise, it is low. Here we can apply the 0, 1 case. At the time, the output is 0. In this case, A is equal to 0 and B is equal to 1. Then the output sum is equal to 1 and carry is equal to sum is equal to 1 and carry is equal to 0. In this adder, we can add 2 bits at a time. Then the adder is known as the half adder. Okay. Already we can discuss already I told you, digital electronics means digital electronics is a branch of electronics which can deal with the generation, processing and storage of digital signals. This helps in analysis and simplify the logic expressions, analysis. Okay, this helps in analysis, design for the circuit diagram and construction of digital system. This helps in analysis, design and construction of digital system. Here we can do the analysis and design of half adder circuit diagram and constructor. We can use for the XOR gate. We can use for the XOR gate IC number 7486 and AND gate. We can use for the 7408. 7486 IC and 7408 IC we can construct for the breadboard. Okay, then the circuit acts as a half adder circuit. Okay, thank you.